That's it. So,
Sir would have to be one window. I don't know. I don't think so.
So we'll keep the noise down so we can see the signals better.
Right.
Okay, we'll get back to our Frank-Hartman principle. We already saw what it meant. We saw how powerful it is in explaining the intensities of vibrational transitions in electronic spectroscopy. So essentially meaning that you are making a jump from one electronic state to another, which in effect means you are removing an electron from one molecular orbital and putting it into another molecular orbital. So you have changed the electronic distribution. But while you have done that at the same time, you are also making transitions between vibration levels in the ground electronic state to vibration levels in the excited electronic state. The question we ask ourselves is, are there selection rules for this? We know selection rules for intra-vibrational transitions within an electronic state. Delta V plus minus 1 for harmonic and anything else for an harmonic, but with significantly reduced intensities. Very clear selection rules. But when it came to looking at transitions between a set of vibration levels in the ground electronic state or one electronic state to a set of vibration levels in another electronic state, the rules were not very clear. And we went through the transition probability integral and we wrote that using the Born-Oppenheimer approximation. We split the dipole moment also into a nuclear part and electronic part. And finally, what did we end up doing? We had one integral that just went away because of the orthogonality of the electronic wave functions. There was another integral, this is a double integral that survived. And that double integral essentially looks like, I'm not going to erase this. We saw this, and we also said that this part of the integral is actually something that tells me whether the transition from one electronic state to the other electronic state is at all allowed. If this guy goes to 0, it simply means I am not seeing an electronic transition from that electronic state to the other electronic state. Meaning the low potential zero, I just can't make a transition. Forget the discussion about vibrations. I can't even get the electron from an orbital corresponding to this potential and put it into an orbital corresponding to this potential. I can't even do that. So this question of whether the vibrational transitions are allowed does not even arise. Because the first integral actually tells me whether the selection rule is going to allow me to jump from one electronic state to the other. If this is non-zero, that means I can potentially make a jump from here to here. And then the question is asked, where from here can you jump to where to here? Can I go from V0 to V0 or V0 to V1? That question arises only after you have taken care of this. If this is 0, this doesn't matter what the number is. The whole thing is still 0. If this is not 0, then you have to worry about the second part, which is the overlap integral, the vibrational wave function overlap. And we said that that vibrational wave function overlap, the square of that, actually tells me the probability of the transition being made from one vibration level to the other. Okay? And we also give a name to that, we call that as the Frank-Hartman factor, FCF. And you will see spectroscopists always talking to you in terms of Frank-Hartman factors, Frank-Hartman overlap, Frank-Hartman regions, and so on. And we will try to clarify a few of these issues today before we go any further. And this is therefore the factor that really tells me from a given vibration level to which vibration level I can actually go to. So it's not a selection rule, mind you. A selection rule is very fixed, delta V plus minus 1. And it doesn't matter whether I go from 0 or 1 or 2 or 10. If it is plus minus 1, I can only go from 10 to 9 or 10 to 11. Finish. If it is 20, 21 or 19. Finish. This is not like that. This integral actually tells me if I give you the initial state, you have to take the wave function and then sort of compare all the upper state wave functions and see with which one of them is going to make the best overlap. And the one with which it makes the best overlap is the one that is going to be greatly around. The probability is going to be great in that situation. So you really have to take it case by case. And that's the reason why we don't call it as a selection rule. Selection rule is not case by case. It's a rule, delta V plus minus 1. Whereas here, given two vibration levels, I have to see whether the wave functions overlap. If they overlap, I have a transition. If they don't overlap, I don't have a transition. If I give another set of vibration levels, again compare the two vibration wave functions. And therefore, we call this more as a propensity rule and not a selection rule. And of course, the square of this function, of this overlap integral, is basically the Frank Harmon factor. And as I said, it's got a connotation of a probability. So if that square of that integral turns out to be 1, what does that mean? Starting from that level, going to the other level, probability is 1, meaning that's all that can happen. Starting from B0, and we saw this yesterday. If this function and this function are nearly identical, both in shape as well as in location, then what happens to the overlap? And how do you calculate overlap? Well, you could do it in one way. Just take this function, bring it down, and keep it on this and see how much it overlaps. If they overlap completely, then the probability is going to be 1. And if the probability is 1, it simply means going from here to here carries all the probability. You have run out of probability after that. Meaning I can't go from here to anywhere else because I just won't have any probability there. I've already used up everything. But if going from here to here, if this overlap with this, let us say is like this, then what's the overlap part? It's just this part. Over here there's no overlap, here there's no overlap. So which means the square of that integral will not be 1. It might just be 0.7, 0.6 or what have you. If I have 0.6, it simply means there's a 0.6 probability that I can go from this level to this level. Which therefore means I still have a 40% probability of looking at other possibilities. And you go looking for those transitions. And this is how these analyses are basically done. Now let's look at these wave functions in a little more detail. Okay. If you want to look at the pendulum problem, okay, if I had a pendulum moving back and forth, and then we said, we might have discussed this last one or two also. If I had a pendulum going back and forth, and let's say I do it in a dark room, I let it go back and forth, and I just turn the lights on at some random time. And you have to predict for me where you would expect to see the pendulum at that time as it goes back and forth. Where would you bet your money? I'll give you 3 locations or 5 locations. Where would you bet your money on seeing the pendulum when the lights are turned on at random? A or E? Anybody disagree with that? Nobody. And maybe we discussed it already? No. Okay. Why A or E? Because the pendulum as it goes, it's going to spend a little more time because it goes up there, it's sort of already slowing down. It spends a little more time and then comes back, spends a little more time. So if you are a good gambler, you would actually want to bet on this being here and here. Not that you would win it, but you have the best chances of winning it. Because the next time the lights on, the pendulum could be here. Because it's all probability. But if you played this game a million times, and if you kept on betting A and E, then you would win. But if you just played it once or twice, then you have no clue as to which is going to be the situation, and therefore you won't even know whether you're going to win or lose. But if you played this game a million times, and if you kept on betting A and E, then you're likely to make money. Because the probability of seeing this over here is the greatest. And we know why. Because it simply spends more time at the edges. If you take this concept and bring it to the vibrational system of a molecule, and if I told you, here's the molecule, and V equal to 0, it vibrates between this and this. So this and this are the equivalents of A and E. So where do you think the molecule will spend the most time on its travels? Again, the same thing, you would expect to see the A and E, but then of course this is a quantum system. It does the most ridiculous things. You already seen that in the particle in the box. In the particle in the box, what's the N equal to 1 wave function look like? Right? But if you look at it classically, if I had a particle inside a box like this, I rattled it. Where is the probability going to be for this? It could be anywhere. The probability is actually equal that the particle can be seen anywhere inside this box. But that's not the case in the quantum system. In the quantum system, for some very strange reason, you expect to see that particle somewhere in the middle. Because the probability, when you go to plot it for a particle in the box, looks like totally mind-boggling. Don't ask me why, that's the way it is. And we have experimental evidence from many systems that that's the way it behaves. That's why we always say we don't know why quantum mechanics works the way it does, but it just works the way we know how it works. There is no earthly reason I can ever give you as to why the system is sitting more often than not in the middle and not at the edges, whereas in a classical particle in a box, particle can be anywhere inside the box. There is no reason as to why it should be in the middle, on the way over here. So you already have been introduced to ridiculous behavior in quantum mechanics. We're going to get one more today. When you look at this system here, vibration system, V equal to 0 wave function. If you were to plot, this is what it looks like. And what does this mean? It simply means that the greatest probability of finding this vibrating particle or the vibrating molecule, where is the probability the greatest? Not at the edges, but somewhere out here. Point a gun at me, and I won't tell you, I won't know how to answer this question. Why is it that way? That's the way it is. But we have experiment to prove that that's the way it is. But if I take this particle and go up to the next level, what happens to it? What does the vibration wave function look like? Getting better, because now it's starting to move to the edges. So you have to plot the probability for this. It will look like so you can see the probabilities have gone to the edges. And by the time I go to V equals 40 or V equals 100 or something like that, upstairs. So really, if it is let's say V equals 20, how many nodes must I have in that function for V equals 20? 20 nodes. V equal to 0 has 0 nodes, V equal to 1 has 1 node, V equals 20 must have 20 nodes. So, if this is V equal to 20, I must have 20 nodes, don't count. That's why don't count, because I have not counted it to be 20. But you will have 20. But you can see what happens over here. As I go further and further, higher and higher, the particle actually starts to behave like a classical particle. And therefore you will see that the probabilities really peak up at the edges. So right here it behaves more quantum mechanically, and as you go further up, it behaves classically. So the wave functions actually look like these, and these are the wave functions that you must really take when calculating those prime quantum factors. So what is now the treatment, or what is now going to be the conclusion when I'm going to apply the prime quantum interpretation? Let's say I go from here. Here's my wave function, and here's my wave function. If I'm going to go from here to here, is this going to be allowed? Yes, it's going to be allowed. Why? Because if I take the point when the probability is the greatest, what does that mean? It means to a very large extent the particle is going to spend a much larger time in its vibrational traverse somewhere over here, and therefore when I make a transition, it is likely that more often than not I am making a transition from here. Nothing excludes or precludes me from making a transition here, but the probability is so small. So if I make a million transitions, most of them will be from here, so that is where the probability is the greatest. I go from here to here, and where am I going? Here. And at this point, what is the probability here? Is the greatest. So if I go from a point of greatest probability to a point of greatest probability, that's really going to be allowed. But if I go from here to, let us say, to here, what does that really mean? I'm going from a high probability to a point at the upper state vibration level where the probability has to be low, which means you really can't find the molecule there most of the time. And therefore, this transition is not going to be so favorable. It's the same thing as saying that this wave function and this wave function will not give me a good overlap. That's basically what it means. Because if I take this wave function and overlap with this wave function, what's going to happen? There's a part of it which is positive, there's a part of it which is negative, and they will kill each other. And therefore, this onto this overlap is going to be nearly zero. You can look at it more physically and say, I'm trying to go from a point of high probability to a point of low probability, and that isn't really favorable. High to low, not favorable. Low to low, not favorable. Low to high, not favorable. What's going to be favorable? High to high. So, if I want to go from this state to this state, I better be sampling both potentials in regions where the probability is really going to be high. Supposing I have this situation like this. I go from here. I'm going from a region of high probability to a region of not so high probability. Therefore, this transition will be there, but not so great. But look at any V equals 2. What happens now? I can really go from V equal to 0 to V equal to 0. There's some probability there. I can go from V equal to 0 to V equal to 1 because there's a good probability. And I keep going up. Maybe I can see V equals 2, V equals 3, and so on. In other words, what do I see now? I see a progression. I see a progression. If two potentials were very similar looking and located one on top of each other on the internuclear axis, what would I see? Sequence. 0 to 0, nothing else. 1 to 1, nothing else.